Although machine learning has made a lot of progress over the ages, the problem of data imbalance still haunts the different applications of machine learning. For example, a classifier trained on an imbalanced dataset like this will have a bias towards the majority dataset, thereby reducing the accuracy of the classifier. Also, there is a problem of small disjuncts or within class imbalances, which creates small clusters of the minority class within the dataset, reducing the accuracy of the classifier even further. One of the techniques that has been proposed over the years is the synthetic minority oversampling technique, which basically takes one of the minority data points and one of its closest neighbors, joins a line between them and creates a new point in between. And this is how it creates many such different synthetic data points and adds these data points to the minority population, thereby adding a semblance of balance to the data set. However, if you look at this diagram, the points B and P belonging to the minority dataset, when they create a new point, it adds more noise because they are in an environment or in a space which is crowded with majority data points. So this is a problem with SMOTE, and there has been many work which has been done using the SMOTE as the basis, and our work is called the K nearest neighbor oversampling approach, which has three different steps while creating a minority dataset. First, it tries to find the critical minority dataset. What does that mean? So out of all the minority dataset, we try to find a subset which is an important or a critical subset of the minority dataset, which is then used to create the artificial data points. And then for every data point that is created, we have a step of validation to make sure that this new point that was created is actually adding value to the data set. So the critical data is identified using its every point's distance to its kth nearest neighbor, and then filtering the points which are very close to its kth nearest neighbor. K could be any value 2, 3, 5, and removing or not using the points which are really far away from its kth nearest neighbors. This helps us in removing or rejecting outliers while choosing the minority datasets that are going to be used for augmentation. It also helps us in rejecting misclassified or mislabeled datasets which will not be used while creating the artificial dataset. The actual step of creation of artificial data is something like this. We take a source point, we say our number of neighbors is 3. So what we do is we join that point to its first nearest neighbor and create an artificial data point. Then we join this newly created artificial data point with the second nearest neighbor of the original source point and create another point. Then we join this newly created artificial data point to the third nearest neighbor of the source point and put another point in between, and this point is our prospective new artificial data point. Next, what we do is, with the artificial data point just created, we apply the K nearest neighbor algorithm to check whether this newly created point is actually a good member of the minority data point or not. If it is, then we allow it to be within the minority samples or we reject it. So here you see some examples of the output of the augmentation algorithm. If you look at figure A, the green circles are the majority data points, while the orange triangles are the minority data points, and the blue squares are the artificially created data points. So between figure B, C, and D, what is changing basically is the value of D, which is 0.3, 0.5, and 0.9. This is basically saying what is the proportion of the minority data point that we are using. In this case, we are using 30% of the minority population, whereas in this case, in the case of D, we are using the 90% of the minority population. But it's interesting to note how in all cases the noise or the outliers are successfully ignored while creating the minority data points, artificial ones. Here we see some comparison with existing state-of-the-art oversampling approaches. And the last two diagrams are the effects of KNNOR, with K which is the number of neighbors, is 2 and 7. So as you see, since the K is 2 in figure number F, the minority data points newly created are close together, whereas when K is 7, the minority data points are spread out further. This is another example of the result of the KNNOR algorithm with different parameters. Let's look at figure A and figure D. Here distance threshold is 0.1 in both cases, which means that we are using 10% of the minority population, but the number of neighbors is 2 and 7. As a result, you can see in this case the newly created artificial data points are very close to each other, whereas there is some kind of a spread here. Again, let's check the figure numbers B and C. Distance threshold is 0.9 in both cases, which means that we are going to use 90% of the minority population. However, number of neighbors is 2 and 7 in the two cases, which means that in case of figure B, only 2 nearest neighbors are used, whereas in case of figure C, 7 nearest neighbors are used. As a result, you can see there's a different kind of a spread in both the diagrams, in both the outputs. However, it's interesting to note that in both cases, in all cases, the outliers and the noise is ignored, and this gives us this allows us to create different patterns or different distributions of data, thereby making our classifier more robust. What we did next was we compared the performance of our algorithm on 19 imbalanced datasets using training 4 different classifiers on the balanced dataset using our algorithm, and then checked 4 different metrics. We compared it with the 10 state-of-the-art algorithms that I've mentioned in the previous slide, and we saw that KNNOR is performing better in almost all the cases. For example, in case of the metric AUC, the KNNOR is coming first more than 40 times. In case of the metric F1, KNNOR is coming first more than 30 times. In case of all the cases, basically, KNNOR has the highest number of first ranks, followed by other algorithms. In case of programming this, we have already published this as a library, so you can simply do pip install KNNOR to install this into your Python package. Then you can do from KNNOR import data augment. This will import the library, and that is how you use any other machine learning algorithm. You just have to create the object of the data augment KNNOR class using KNNOR equal to data augment.knor, and then knor.fit resample x comma y, which is your original data set, imbalanced data set, and you get x new y new, which is your balanced data set. So initially, if you had 212 minority data points, after calling this function you will have 357 data points, which is same as the number of majority data points. Now you might ask, how do we include the different parameters like number of neighbors and distance threshold and all that? It's the same function, fit resample. Besides x and y, you can also include these different parameters. If you don't pass them, the algorithm tries to calculate and compute at the optimized values, but you can always pass in different parameters and see how your classifiers are performing on different values. So number of neighbors is equal to 10 means that it will be using 10 nearest neighbors while computing the artificial data point. Maximum distribution distance point 0.001 means that between any 2 points while creating the new artificial point, it will only allow a distance of 1 by 100 of the distance of the 2 points. Proportion minority of 0.3 means it's going to use 30% of the minority population, and final proportion of 2 means that it's going to create the final number of data points is going to be twice that of the majority data set. So initially your majority data point you had 357, and the final distribution you'll have twice that. So this is how you can use the same algorithm with different parameters. Now this research has been published in Applied Soft Computing, which you can go and check. The source code is present in GitHub with some example notebooks, and the documentation is also present. If you use our algorithm, then you can cite our work using this citation. I hope it is of use for your research and for your application, and thank you for watching.